All right, so the problem we're looking at is problem 68 in section 2. The problem reads, David is driving at a steady 30 meters per second when he passes Tina, who's sitting at rest. Tina begins to accelerate at a steady 2 meters per second squared at the instant David passes her. And the two things we're looking for is how far does Tina drive before passing David, and what is her speed when she does. So let's start by writing down our knowns. Let's start with our knowns for David. So our initial time, just set this at 0 seconds, the moment when David initially passes Tina. And our final time, when Tina speeds back up enough to pass David, we're not sure. We don't know that yet. The initial position, let's also just set that at 0 meters, because that's the beginning of the problem. And our final position, again, we don't know that. Now, David's velocity, in the problem, it reads, David is driving at a steady 30 meters per second. That means David's velocity doesn't change. So his initial velocity and his final velocity are going to be the same. That's going to be 30 meters per second. So I'm just going to write velocity 30 meters per second. And because the velocity doesn't change, that means his acceleration must be 0 as well. Now what about for Tina? Well, the time, these are going to be the same. 0 seconds, and again, the final times, we don't know that yet. In terms of x initial position, it's the same position. Again, it's the same x initial position, so we're at 0 meters. And the x final will also be the same x final, so we don't know that either. Now, Tina, however, while David had a constant velocity, Tina's velocity changes, right? Because in the problem it says she accelerates at a steady 2 meters per second squared, which means that her velocity is going to change. Now her velocity, her initial velocity, in the problem states she's sitting at rest in her car. So that's going to be 0 meters per second. And her final velocity, when she passes David, we don't know that yet. But her acceleration, we do know that. The problem states her acceleration is a steady 2 meters per second square. So there's no jerk. We're doing constant acceleration here. So let's look at, just a rough example of what this graph is going to look like. Both of them start at time in seconds. Both of them start at time 0 and position in meters, also 0, right? That's just how we decided to set up our origin here. Now, David goes at a constant 30 meters per second, so we know that the slope of his line is going to be constant, and it's going to be 30, right? So I'm going to just pretend this is the slope of this line is going to be 30. And this is David. Now Tina's position, the slope of her graph is going to be a curve because the slope is changing. It's constantly going up because we have this positive acceleration. So it starts at 0, right? And then the slope gets bigger and bigger and bigger. Now this is the part we're looking for. This is going to be that t final, x final, where, again, Tina and David are at the same spot where Tina passes David. So this spot is where, in the initial problem, David passes Tina. So the first thing the problem asks is for how far does Tina go before passing David? That means we're finding the point where David and Tina's final positions are equal. So let's look at the equation for finding the final position. That's going to be x final equals x initial plus velocity initial times t plus 1/2 acceleration t squared. Now, if we look at this equation, we actually have a lot of this for both David and Tina, right? X initial, we've got that. We actually set that ourselves to 0. Velocity initial, well, David's velocity is constant the whole time, 30 meters per second. And Tina's initial velocity we know is 0. Time, that we don't know. That's going to be this final time, right? Because it's actually a change in time, but since our time starts at 0, and delta t equals t final minus t initial, if this t initial is 0, then the delta t just equals the t final. And then acceleration for Tina we know is 2 meters per second squared, and for David we know is 0 meters per second squared. And then again we've got that t final. We can't solve for that. But we have two versions of this equation with two sets of values, one from David and one from Tina. And we've got two variables that we don't know. One of them is already over here, right? So we could just sub this half of this equation out for the values of the other person. So for example, for David, x initial is 0 meters plus v initial is going to be 30 meters per second times t final plus 1/2 acceleration is 0 times 0 meters per second squared times t final squared, right? And we can set that as equal to Tina's values for the same thing. So Tina's initial position is also 0 meters, plus her initial velocity is 0 meters per second, times, again, we don't know what this t is, right, t final, plus 1/2 her acceleration, 2 meters per second, times 2 meters per second squared, times t final squared. So we can simplify this quite a bit, right? That's 0, that's 0, that's 0, and that's 0. So we've got basically 30 meters per second t final equals 1/2, actually 1/2 times 2. This is just going to be 1, so we don't need to have that at all. Just t final squared meters per second squared. So we can continue to solve this by moving this half over here. And then we've got 0 equals, I'm going to rewrite this a little bit differently, but 1 meter per second squared times t final squared minus 30 meters per second t final. Now, this looks like a quadratic equation. So we can actually solve for t by plugging this into the quadratic equation. And what we get doing this is that t equals negative b. So b is our 30 meters per second. So or negative 30 meters per second. Negative of a negative is positive. So that's going to be 30 plus or minus the square root of b squared is 900 minus 4ac. So a is 1, but c is 0. So, 4 times 1 times 0, it's going to wind up to be 0, all over 2a. So our a is 1 here, so that's just going to be 2. So this actually looks like 30 over 2, that's 15, plus or minus the square root of 900, right? Because this is 0. We actually know square root of 900 is 30 already. But then 30 over 2, that's 15 again. So this is going to equal 0 or 30. And we're solving for t, so that's seconds. Now, we know that 0 is a valid answer. That's given to us right in the graph here, right? They cross each other. That means the two lines have equal values at 0. So I'm pretty confident in this answer, 30 seconds. So this is going to be 30 right here where they meet. So now that we know that we've got 30 seconds as this elapsed time here, we can solve for the final position for Tina by plugging 30 back into this equation here. So our x final is going to equal x initial, that was 0. I'm not even going to write it in. Plus v initial, again, 0. Not going to write it in. Plus 1/2 a t final squared. Well, we know the t final is 30 seconds, so we're going to have, and this 1/2 a, we remember, is 1 meter per second squared. So we've got 1 meter per second squared times 30 seconds squared. That's going to be 900 seconds squared. So here, we're dividing by second squared, multiplying by second squared. Those cancel out. So this is going to be 900 meters. So we can now fill this stuff in up here. 30 seconds, 30 seconds, 900 meters, 900 meters. So the first part of the question is now answered. How far does Tina drive before passing David? That's 900 meters. Now, what is her speed when she does? That's the second part of the question. So we can find her final velocity via the equation v final equals v initial plus a times t. Now we know the v final, we're looking for the v final. We know the v initial is 0. So v final equals 0 plus the acceleration, we knew that from the beginning, 2 meters per second squared, times the elapsed time, that's going to be 30 seconds. We've got seconds divided by seconds squared, that drops down to meters per second, and that's going to be 60 meters per second, her final velocity. And we're done.